Hello, in the previous clip we undertook 2 degree of freedom control design to achieve robustness to variation of plant parameters. In the example that we considered, we assumed that the gain of the plant was uncertain and it could increase by a factor of 3 or drop to 30% of its nominal value. In other words, the gain could change by a factor of 10 from 0.3 all the way to 3, while its nominal value was assumed to be 1. So, we saw how we could go about designing a 2 degree of freedom control system that could achieve a specified amount of robustness to the variation of the plant's gain. At the heart of this approach is to locate a pair of zeros near the place where the dominant closed loop poles of the overall closed loop system is supposed to be located, and these zeros have the effect of restricting or pinning the variation of the closed loop poles when the plant's gain changes. But then when one places zeros, in order to achieve causality, we also have to have controller poles that need to be placed, and we saw that we couldn't place these controller poles anywhere. There were stability concerns that arose based on the position where we chose to locate the controller poles, and we found that they had to be located at least some distance away from the imaginary axis, from the origin of our complex plane, in order for the closed loop system to be stable, or for the closed loop poles on the other branches of the root locus to not have the poles on the right half of the complex plane. So, although we considered only the variation in gain of the plant in our design in the previous discussion, in principle the same approach can be adopted to address variation of several other parameters of the plant. For instance, if the plant's pole location is uncertain, it is possible to design a robust control system whose overall response does not change significantly in response to the uncertainty associated with the pole location of the plant. Likewise, if the pole and the gain are both uncertain, once again we can come up with a systematic design strategy that will allow us to achieve the specified amount of robustness to variation, independent variation of both the gain of the plant as well as its pole location. Now, if the plant has multiple poles and each of them are uncertain and even the gain of the plant is uncertain, then the control design strategy that we would be talking about allows us to handle even such fairly sophisticated and challenging problems using the techniques that we talked about in the previous lecture. So, what we shall do today is to look at one of these problems, namely uncertainty associated with the pole location of the plant. Having solved this kind of a problem in the past, in the previous clip we looked at how we attack the problem associated with designing a robust control system that achieves that minimizes the sensitivity of the dominant pole to the variations in the gain of the plant. The steps that would be adopted in this design are also quite similar, and many of the steps that we would undertake would follow exactly along the same lines, the ones that we talked about in the previous clip. So, what we shall do first is we shall state the problem, then we shall underscore the important steps involved in the design, and rather than go through each of these individual steps in detail exactly as we did in the previous clip, we shall focus on what is new and what is it that needs special attention, and discuss only those aspects of the design that are new to the new problem specification, and the other steps might remain the same. So, we shall briefly touch upon what the other steps are, but we shall not get into the details of solving the other design steps of the problem. So, if we look at the problem that we are considering in today's in this clip, we once again are asked to design a 2 degree of freedom control system to achieve robustness to variation in plant parameters. So, the plant that we have considered is exactly the same plant that we looked at in the previous clip. P of s is equal to 1 by s times s plus 1 times s plus 2, that was the plant. But in this example we have assumed that the pole at p equal to at s is equal to minus 1 is uncertain. So, the nominal value of p in this expression here is equal to 1. So, nominally the plant has one pole at the location s is equal to minus 1, but this pole can lie anywhere between 0 and 2. In other words, the pole can lie at the origin or it can go all the way to s is equal to minus 2. So, it can lie anywhere on the real axis of the complex plane between s is equal to 0 and s is equal to minus 2. So, once again here we have a plant that is uncertain. In this case there is no uncertainty associated with the gain, unlike the previous example that we considered in the last clip. So, the gain is always equal to 1. So, there is no uncertainty associated with that, but the pole location is uncertain. And the location of the dominant closed loop poles is expected to be the same as what we had in the previous clip. They are expected to be at minus 1.5 plus minus 2j. This, as we discussed, in the absence of uncertainty in the Planck's model, we can use 1 degree of freedom control design to locate the closed loop poles at this particular pair of points. But the problem arises when one wants to restrict the variation of the dominant closed loop poles, which are nominally located at minus 1.5 plus minus 2j, when the Planck's parameter, in this particular case when the Planck's pole changes or when there is uncertainty in the Planck's pole. This problem cannot be handled using 1 degree of freedom control design, and one has to adopt a 2 degree of freedom control design. Now, what has been specified as far as the variation in the dominant pole is concerned due to the variation in the Planck pole location is that we want the variation in the closed loop pole at the point minus 1.5 plus minus 2j to be at most 0.04 units. So, it might wander about in the complex plane, but if one computes the maximum distance that it travels, then that distance should be less than or equal to 0.04 units. So, this is the problem specification, and as we have been discussing, the trick that one adopts in order to restrict the variation of the closed loop pole at 1.5 plus minus 2j due to the variation in the Planck's location is to place a controller 0 near the place where the dominant pole is expected to be located. So, we have the dominant pole at minus 1.5 plus 2j, another pole at minus 1.5 minus 2j. So, we locate two controller zeros z and z bar quite close to these the locations where PCL naught and PCL naught bar are located. And our first step in the design is to determine the exact position of this 0 in the complex plane, or equivalently we can try to determine the distance of this 0 from the point PCL naught, whose coordinates we know very well, and the angle of the 0 with respect to the point PCL naught. This will be the first two steps in the design. Next, we have, since we have had two zeros for the controller, in order for the controller to be a causal transfer function, the denominator polynomial of the controller should also have at least the same degree as the numerator polynomial, which demands that our controller should have at least two poles, and these poles we have called P4 and P5, and we assume that these poles have been placed very far away from the origin. So, the second step in the design after locating the 0 is to determine the positions of these poles P4 and P5, because these poles result in extra branches to the root locus of the system, of the open loop system, and the poles that lie on one of these pair of branches could potentially become unstable when the gains are very high. So, one has to be mindful of the location of these poles and ensure through appropriate design that the controller poles are placed sufficiently far away that for the kind of variation in the Planck parameters that we would have in this case, the closed loop poles on these branches will not become unstable. The third step is to complete the feedback controller design, and that is to determine the gain of the feedback controller. So, we will be able to, the first two steps will allow us to determine the structure of this controller. It would have two zeros z and z bar, the specific positions of these zeros would be identified, it would have two poles. Assuming that these poles are coincident, then we would have the locations of these poles determined in the second step. The next step is to determine the gain of the controller. If one does that, one is done with the design of the feedback controller C. The final step is to determine the pre-filter's structure. The pre-filter exists in order to cancel the poles, so that the overall transmission function relating the output to the reference will not have the terms s plus z and s plus z bar in the numerator of the transfer function, and that will allow the dominant dynamics to be determined by the points PCL naught and PCL naught bar. So let us write down the different steps. The first step is to locate the distance of the 0 from the point PCL naught. Let me call that distance as x. So locate z with respect to PCL naught, which is the location of the dominant closed loop pole. In this case it is minus 1.5 plus 2j. So in other words, we have to determine the distance x. That is the first step in the design. The second step in the design is to determine the orientation of z with respect to the point PCL naught. That is the second step. The third step is to determine the positions of the poles P4 and P5. So assuming that P4 is equal to P5, so you have therefore coincident poles for the controller, determine the location of P4. The fourth step is to determine the gain of the controller. Feedback controller, and this would complete the design of the feedback controller. The next step is to determine the structure of the pre-filter, and that would complete the design of the robust control system. Now among these different steps, we note that in order to determine the distance of the 0 z from the point PCL naught, or equivalently to determine the distance x, we need to know exactly how the closed loop pole PCL wanders about when the plant's parameter changes. In this case, the plant's parameter is its pole location. So there is one pole that is whose location is uncertain. So when this uncertain pole's position changes, in what particular manner does the closed loop pole's position vary? This is something that needs to be determined, and this is something that is specific to the particular parameter that is varying. So we have to undertake this design step in detail once again, and we cannot borrow this from our discussion in the previous clip. When we come to the second step here, determination of the orientation of z with respect to PCL naught, you will notice that we can directly borrow the steps that we adopted from the previous example. So in the previous example, to remind you, we assumed that the points P4 and P5 are very far away from the origin, and we assumed therefore that they do not contribute significantly to the angle at the point PCL naught. Hence we computed the angles subtended by the other poles and zeros of the open loop system, namely P1, P2, P3, Z and Z bar, and equated that to minus 180 degrees. This allowed us to get the angle that the 0 Z had to subtend at the point PCL naught for the point PCL naught to be a point on the root locus. Now this exact same procedure can once again be adopted without any modification for this new design as well. So even when we have this other parameter that is varying, the point PCL naught is going to be a point on the root locus, and hence the angle criterion has to be met at the point PCL naught, which means that the sum of the angles subtended at PCL naught by P1, P2, P3, Z and Z bar should add up to minus 180 degrees. The only unknown here will be the angle subtended by the point Z at the point PCL0, because the angle subtended by the point Z bar at the point PCL0 is approximately plus 90 degrees. So assuming once again that the angle subtended by P4 and P5 at the point PCL0 is negligible, we can determine the angle subtended by Z at the point PCL0. In the first step of the design, if we are successful in determining the distance x, and in the second step if we know the angle of this point Z with respect to PCL0, then the two together will allow us to fix the point Z. If the point Z gets fixed, the point Z bar also gets fixed. So the second step of the design is essentially going to follow the same logic and arguments as the corresponding step that we undertook in our previous design example when we had uncertainty in the plant's gain. So in this clip therefore we shall not look at this in great detail, we shall just assume that we can apply the same steps and get the answer for this second part. Coming to the third part, in the previous example when we assumed that P4 and P5 are coincident poles, we then drew a big picture root locus where we noticed that we could lump the 3 poles of the plant and the 2 zeros of the controller that were near the origin as one equivalent single pole, and therefore we had a simplified root locus in this big picture where we had 2 controller poles far away at the point P4 and P5 which we assumed to be coincident, and a single pole near the origin. And using this picture we could determine the gain at which the root locus crossed the imaginary axis, and we could ensure that this gain was less than the gain of the maximum gain that the overall open loop system could assume. And the same steps can in principle again be adopted in this case as well. Hence we shall not discuss in great detail about determination of the points P4 and P5, because the same steps shall be adopted as what we had done in the previous clip. Likewise for the fourth and the fifth points also, once we have determined the locations of the points P4, P5 and Z and Z bar, then we know the structure of the controller, the structure of the plant is already given to us, therefore we can determine the gain K of the controller by using the equation K is equal to minus 1 by Cp evaluated at PCL0, and with that our feedback controller design would be done. And the final step is to determine the structure of the pre-filter, and we noticed that in the previous example our pre-filter had the structure F is equal to Z Z bar divided by S plus Z times S plus Z bar, and this structure ensured that the pre-filter transfer function cancelled the zeros of the transfer function for the feedback part of the system alone, and that ensured that the points PCL0 and PCL0 bar were the dominant poles of our closed loop system. So steps 4 and 5 therefore are also identical to the steps that we undertook in the first example. Hence the first step alone is something that is new and that has to be investigated for this particular case where we have the plant's pole to be uncertain instead of its gain, while the other steps are exactly identical to the steps that we undertook in the previous design which we discussed in the previous clip. So viewers of this clip are urged to look at the design steps in the previous clip in order to understand how to undertake the steps 2 to 5 in this particular design example. Although the numerical values might be different in each of these steps, the procedure that one employs is exactly the same. The procedure and the logic are no different from what we discussed in the first example. So in this clip therefore we shall focus only on the first step of the design, namely the technique that one might adopt in order to locate the point Z with respect to the point PCL0. Since the point PCL0 is a point on the root locus, we would have the root locus equation to be valid at the point PCL0. In other words, K will be equal to minus 1 by Cp at the point PCL0. and we know that this is going to be equal to minus 1 by, we know that we have a controller with two zeros, which is S plus Z and S plus Z bar, and it has two poles, and we have assumed that these poles are coincident. So S plus P4 the square, and our plant is given by 1 by S times S plus P times S plus 2, and this entire thing is evaluated at PCL naught. S is equal to PCL naught. So if we were to undertake some simplification, this would be given by K is equal to minus of S times S plus P times S plus 2 times S plus P4 the square divided by S plus Z times S plus Z bar. In the nominal case, we would have K nominal to be equal to minus of S times S plus 1, because the nominal value of the plant pole is at S is equal to minus 1 times S plus 2 times S plus P4 the square divided by S plus Z times S plus Z bar. Now we note that when the plant's pole location changes, it has absolutely no effect on this gain K, because the gain K is independent of the pole location of the plant. Hence we would have K nominal to always be equal to K regardless of where the actual plant's pole is between the limits that we have indicated, between the limits S is equal to 0 and S is equal to minus 2. So regardless of where between these two limits the point S is equal to minus P is located, the root locus equation will be valid with the same gain K, and hence we would have that minus of S times S plus P times S plus 2 times S plus P4 the square divided by S plus Z times S plus Z bar, and this would be evaluated at the location where the dominant closed loop pole would be located, and when P is not equal to its nominal value of 1, then the closed loop pole will not be located at PCL naught, it will be located at some point PCL. So this is going to be equal to minus of S times S plus 1 times S plus 2 times S plus P4 the square divided by S plus Z times S plus Z bar, and this is evaluated at the point PCL naught. In order to make further progress, we shall depend upon the geometric interpretation of the terms S, S plus P, S plus 2 and so on evaluated at the point PCL naught. Now if we look at the term S evaluated at the point PCL naught, it essentially represents the complex number starting at the point P1 ending at the point PCL naught, and hence it would be P1 PCL naught. So this is the term S. Similarly, the term S plus 1 evaluated at the point PCL naught will essentially be the complex number starting at the point P2 naught, which is the nominal location of the pole that is wandering about, and that nominal location is at S is equal to minus 1. So this distance P2 naught PCL naught represents the complex number S plus 1 evaluated at the point PCL naught. So the second term is going to be P2 naught PCL naught. The third term is S plus 2 evaluated at the point PCL naught, and the point S is equal to minus 2 is essentially the point P3 here. Therefore once again with the same logic we can conclude that the term S plus 2 is nothing but the complex number that starts at the point P3 and ends at the point PCL naught. So the third term is P3 PCL naught. Similarly, S plus P4 and S plus P5, since P4 and P5 are coincident poles, will essentially be S plus P4 the square, and evaluated at the point PCL naught will essentially be give me P4 PCL naught the square. This divided by Z PCL naught which represents S plus Z evaluated at the point PCL naught, and Z bar PCL naught which represents the point S plus Z bar evaluated at the point PCL naught, times minus 1 gives me the nominal gain K norm. Now likewise I would have the actual gain of the system which is going to be equal to the nominal gain to be equal to minus 1 times P1 PCL, because when the plant's pole location changes, the closed loop pole will no longer be located at the point PCL naught, it may be located at some other location. We shall call that location as PCL. Now when this plant pole is at this location, let me call this actual position of the plant pole to be P2, while P2 naught is its nominal position. When it is at P2, let us assume that the closed loop pole will be at the point PCL. So nominally when it is at P2 naught, namely at S is equal to minus 1, the closed loop pole will be at PCL naught. So since the point PCL would also be a point on the root locus, we would have the root locus equation to be valid at this point PCL, and hence the value of S, the complex number S evaluated at the point PCL is nothing but the complex number P1 PCL, and that is what has been written here. Similarly, the complex number S plus P evaluated at the point PCL, where P is the point P2 here, is essentially going to be P2 PCL. So this is going to be the second complex number, and the third complex number is going to be P3 PCL, which essentially represents the complex number S plus 2 evaluated at the point PCL times P4 PCL the square divided by Z PCL times Z bar PCL. So since the plant gain or the controller gain does not change when the plant pole location changes, K will be equal to K nominal. So this equation here will be equal to that equation there. Now we will make one simplification in the second equation. If we look at the point P1 PCL, it represents, as I said, the complex number joining the point P1 to the point PCL. Now if we look at the point P1 PCL naught, that represents the complex number joining the point P1 to the point PCL naught. Now from our specifications we know that the 2 points PCL naught and PCL should not be more than 0.04 units away from one another. If we compare the kind of distances that we have between the point P1 and PCL naught or the point P1 and PCL, these distances are significantly bigger than the maximum permissible distance between the point PCL naught and PCL, because the point P1 is at S is equal to 0, P2 is at S is equal to minus 1 nominally, P3 is at S is equal to minus 2, and Z will be located close to the dominant closed loop pole location, which is at minus 1.5 plus 2j. So these are all distances whose magnitude is on the order of unity. On the other hand, the distance between PCL and PCL naught is expected to be just less than 0.04 units, so which is almost 2 orders of magnitude lesser than the typical distances between the other open loop poles and zeros of the plant and the controller. Hence we can conclude that P1 PCL is approximately equal to P1 PCL naught. So what I can do therefore is the second equation, I can write it as K is equal to minus 1 times, instead of writing it as P1 PCL, I shall write it as P1 PCL naught. And the second term is P2 PCL, and that represents the distance of the point P2 from the point PCL, and I am indicating that by this dotted curve here. So if you notice once again, the complex number P2 PCL is approximately equal in magnitude as well as orientation to the complex number P2 PCL naught, and that is because the points PCL and PCL naught are very close to one another, just 0.04 units away from one another, whereas the distance of the point P2 from both these complex numbers is quite large, it is on the order of unity. Hence I can replace the second term in this expression, which is P2 PCl, with the term P2 PCl naught. Likewise, P3 PCl can be replaced by P3 PCl naught, and P4 PCl can be replaced by P4 PCl naught the square, and in the denominator we would have Z PCl. Now we cannot replace this with Z PCl naught, because by choice we have to place the 0 very close to the point PCl naught, so close that the distance between the 0 and the point PCl naught would be comparable to the permissible variation in the closed loop pole location, namely 0.04 units. Hence, when this point PCl naught wanders to the new location PCl due to uncertainty in the plant's pole location, we cannot assume that the complex number Z PCl would be very nearly the same as the complex number Z PCl naught. Hence, we shall preserve the complex number in the denominator as Z PCl. And the final complex number here is Z bar PCl, and Z bar PCl represents the complex number that connects the point Z bar to the point PCl, and you can see from the schematic here that this complex number is for all practical purposes identical to the complex number that connects the point Z bar to the point PCl naught, simply because once again the point Z bar is very far away from both PCl as well as PCl naught. Hence, I can replace the last term with the term Z bar PCl naught. So now we are in a position to make some meaningful simplification to the expressions that we have written in this slide. If we compare the terms k nominal and the terms k, we see that the first term in k nominal is P1 PCl naught, and the first term in k is also P1 PCl naught after making this appropriate small simplification. Hence, let me circle the terms which are equal to one another. P1 PCl naught is existing both in k nominal as well as in k. The second term in k nominal is P2 naught PCl naught, and the second term in k is P2 PCl naught. These two are not necessarily equal to one another, so I cannot cancel them out, circle them out. The third term is P3 PCl naught in the first expression, and it is also P3 PCl naught in the final expression. The fourth term likewise is P4 PCl naught the square. Here also it is P4 PCl naught the square. So these also are the same in the two expressions, one for k nominal and other for k. In the denominator I cannot remove, I cannot circle Z PCl naught and Z PCl because these two are different. So I have Z bar PCl naught as a second term in the denominator of the first expression, and I have the same term also repeated in the final expression. Therefore, when I equate k to be equal to k nominal, I discover that all these terms simply cancel one another and go away from the equation, and I am left with just a few terms. In particular, I would have P2 naught PCl naught divided by Z PCl naught to be equal to P2 PCl naught divided by Z PCl. Now, what is the geometric interpretation or meaning of this equation? To understand the geometric meaning of this equation, I have written down this expression once again, and alongside it, above it, I have once again the complex plane displaying the locations of the different open loop poles and the desired dominant pole location. On the right hand side, I have separately zoomed in to the area near the 0 z and indicated the point z in relation to the point PCl naught. So let us return to this equation. P2 naught PCl naught divided by Z PCl naught is equal to P2 PCl naught divided by Z PCl. Let me rearrange it a little bit. I would have Z PCl divided by Z PCl naught to be equal to P2 PCl naught divided by P2 naught PCl naught. So this is the equation. Let us look at the geometric interpretation of this equation. So the point PCl would be somewhere here, that corresponds to the closed loop pole position when my point when the plant pole is actually at the point P2, and P2 naught represents the nominal position of the plant pole, which is S is equal to -1, and for this nominal position we know that the closed loop pole will be located at PCL naught, namely -1.5 plus 2j. So in this zoomed in view also I shall locate the point PCL. So it would be located, let us say, somewhere here. Now the term ZPCL essentially refers to the complex number that connects the point Z to the point PCL, that is the complex number. The term ZPCL naught represents the complex number that connects the point Z to the point PCL naught. Now on the right hand side we have P2 PCL naught and P2 naught PCL naught. The term P2 PCL naught represents the complex number that connects the point P2 to the point PCL naught. It is this complex number. Likewise, the point P2 naught PCL naught represents the complex number that connects the point P2 naught to the point PCL naught, which is that complex number. And what this equation here says is that the ratio of these two complex numbers ZPCL and ZPCL naught is equal to the ratio of those two complex numbers, namely P2 PCL naught and P2 naught PCL naught. Now when the ratio of two complex numbers is equal to the ratio of two other complex numbers, what we can essentially say is that the ratios of the magnitudes of these two complex numbers are equal, or in other words we can say that the magnitude of ZPCL divided by the magnitude of ZPCL naught is equal to the magnitude of P2 PCL naught divided by the magnitude of P2 naught PCL naught. So this is one statement that we can make directly from the expression that has been given here. Likewise, what we can also say, if the ratio of these two complex numbers is equal to the ratio of the other two complex numbers, is that the angle between the complex number ZPCL and ZPCL naught should be equal to the angle between the complex numbers P2 PCL naught and P2 naught PCL naught. So what we have on our hands are four complex numbers ZPCL and ZPCL naught. The ratio of the lengths of ZPCL and ZPCL naught is equal to the ratio of the length P2 PCL naught and P2 naught PCL naught, and the angle between ZPCL and ZPCL naught, which is given by this angle theta here, is also equal to the angle between P2 PCL naught and P2 naught PCL naught. So even this angle is theta. So what these two statements imply is that the triangle formed by the points PCL, Z and PCL naught is similar to the triangle formed by the points P2 PCL naught and P2 naught. That is because the ratios of the adjacent sides of one triangle is equal to the ratios of the corresponding adjacent sides of the other triangle, and the included angle in one triangle is equal to the included angle in the other triangle. Hence, as the point P2 wanders about along the real axis from the point S is equal to 0 to the point S is equal to -2, so it describes a triangle that is bounded by the point P1 and the point P3, because the point P3 corresponds to S is equal to -2 and the point P1 corresponds to the point S is equal to 0. So the point P2 can vary anywhere between the points P1 and P3, and therefore it describes a triangle PCL naught P1 P3. Now as this point P2 wanders about, the closed loop pole PCL wanders about in such a manner that the triangle that it describes with respect to the point Z, let me call this point as PCL max and other point other extreme as PCL min. So PCL min corresponds to the closed loop pole location when the plant pole is at S is equal to 0. PCL max represents the closed loop pole location when the plant pole is at S is equal to -2 or coincident with the point P3 in this schematic here. Based on what we have discovered now, namely that the triangles described by the point PCL with respect to the point Z and the point PCL naught is similar to the triangle described by the point P2 with respect to the points P2 naught and PCL naught, we can conclude that when the plant pole wanders about between the points P1 and P3, the closed loop pole wanders about between the points PCL max and PCL min in such a manner that the triangle Z PCL min PCL max is similar to the triangle PCL naught P1 and P3. Now, since we know the coordinates of the point PCL naught and the coordinates of point P1 and P3, we know everything about the triangle PCL naught P1 P3. What we wish to know is the variation of the closed loop pole. That is something that we wish to know, and we wish to constrain it to within 0.04 units as has been given to us by the specification. Now, if the distance from the 0 Z to the point PCL naught is x, then from the similar triangles that we just drew, this distance x is proportional to the distance PCL naught P2 naught, and the distance PCL max PCL min, which is given by this distance here, is proportional to the distance P3 P1. Hence, if we have Z PCL naught to be equal to x, we would have PCL min PCL max divided by P3 P1 to be equal to Z PCL naught divided by P2 naught PCL naught. In other words, since Z PCL naught we assume is equal to x, we would have PCL max PCL min PCL max to be equal to x times P3 P1 divided by P2 naught PCL naught. And if you compute this ratio, you find that for this particular triangle that we have here, PCL naught P1 and P3, this ratio P3 P1, the length of P3 P1 divided by the length of P2 naught PCL naught is equal to 0.97. Hence, this overall distance here is going to be equal to 0.97 x. Now, we have discovered that when our plant pole varies along a straight line on the real axis, our closed loop pole, dominant pole, which is nominally at the location PCL naught, also varies along a straight line, which is given by a straight line on which the points PCL max and PCL min lies. And if the distance of the 0 Z from the point PCL naught is designated as x, the line along which the closed loop pole varies is given by 0.97 x. Now, we have been specified that this distance, namely PCL min PCL max, the magnitude of this, which is equal to 0.97 x, should be less than or equal to 0.04 units. This is our specification. We want the closed loop pole variation to be restricted to within 0.04 units, and this automatically implies therefore that x should be less than or equal to 0.0413 units. So, this equation essentially tells us at what distance we have to position the 0 in order for us to restrict the variation of the closed loop pole to within 0.04 units. It tells us in particular that it has to be located within a distance of 0.0413 units from the point PCL naught. So, this completes the first step in our design. Now, if we come back to the other steps, determination of the orientation of the point Z with respect to the point PCL naught can be done by applying the angle criterion at the point PCL naught. I urge the viewers of this video clip to look at the previous video clip to see the arguments that go behind the determination of the orientation of Z with respect to PCL naught, and subsequently determination of the position of the faraway poles of the controller, namely P4 and P5, once again can be looked up in the previous clip because the steps are exactly the same as what we had in the previous clip. The same also applies for determination of the gain of the feedback controller as well as the structure of the pre-filter. The structure of the pre-filter has already been written out here. If we determine the orientation of the 0 with respect to PCL naught and the distance x, automatically the structure of the pre-filter gets fixed. So, I have computed the locations of the zeros z and z bar for the controller and the far away pole locations for the plant that we just talked about, the plant where the pole location of the plant was uncertain. Nominally it was at s is equal to -1, or in other words here nominally the value of p was 1, but it could change from 0 to 2. And using the design steps that we discussed, we conclude that the controller would be of this kind. The feedback controller would have two zeros z and z bar. The design steps that we just discussed allowed us to determine the distance x of the 0 from the point PCL naught, but the angle criterion can be borrowed from the previous clip, and using that we can determine the exact position of the 0 z. And if you compute s plus z times s plus z bar, what you get is essentially this expression here. The next step is to determine the location of the far away poles of the controller, and this was done using the stability considerations. Once again I urge the viewers to look at the previous clip to understand the different steps, and we discover that the two poles P4 and P5, assuming they are coincident, have to be placed at the point s is equal to -64.5 or beyond that in order for the closed loop system to be stable. Next and the final step in determination of the structure of the feedback controller is to determine its gain, which is given here, and this was determined by using the expression k is equal to -1 by Cp at the point PCL naught. By applying this condition we obtained the gain k. This completes the design of the feedback controller. Now since we know the locations of the zeros z and z bar, the pre-filter structure is quite straightforward, as we discussed a little while ago in this clip, and that is given by this particular structure. The overall root locus of this system is given here. All the poles of the plant and the controller are bunched somewhere near the origin, and the point -64.5 is located here. So we have two branches of the root locus which arise because of these two controller poles at s is equal to -64.5, but by design we have made sure that the closed loop poles that are located on these branches do not cross over from the left half of the complex plane when our plant pole varies about. If we zoom into the area near the origin of the root locus, we can look at the three plant poles s is equal to 0, s is equal to -1 and s is equal to -2. The two locations of the zeros s is equal to z and z bar. So this is the point P1, this is the point P2, this is the point P3, and what I have done on the right hand side is I have shown the step response of a 1 degree of freedom closed loop system. In other words, a closed loop system that does not have a pre-filter due to the different possible positions of the plant pole. So the blue curve here is the closed loop step response of the system when the plant pole is at its nominal position, namely at s is equal to -1. The red curve here represents the step response of the closed loop system when the plant pole is at s is equal to 0, and the black curve here represents the so this is for the case when p is equal to 0, this is for the case when p is equal to 1, and the black curve represents the step response of the closed loop system when the point p is at 2, or in other words the pole of the plant is located at s is equal to -2. And as you can see, the 1 degree of freedom controller does a poor job in restricting the variation of the transient response due to the variation in the plant's pole location, or equivalently the dominant pole of the closed loop system wanders about by unacceptably large amounts when the plant's pole changes. On the other hand, when one plots the step responses of the 2 degree of freedom control system, one sees that all these three curves, the nominal curve which is indicated by blue, the curve when the plant pole is located at s is equal to 0, and the curve, the black curve where the plant pole is located at s is equal to -2, all of them sit almost nearly one on top of another, and this is because the 2 degree of freedom control system has successfully restricted the variation in the closed loop pole PCL naught to less than or equal to 0.04 units when the plant's pole varies. Hence, this again showcases the power of a 2 degree of freedom control architecture in order to achieve robustness in the response of the closed loop system to variation in plant parameters. What we shall do next is to see how we can design a feedback controller with once again 2 degree of freedom control configuration that will allow for achieving robustness against variation of more than one parameter of the plant. For instance, in the first case we shall consider the variation of the plant's gain as well as its pole position, and in the next case we shall look at the variation of the gain along with the variation of more than one poles of the plant. So, if you have uncertainty in more than one pole locations of the plant as well as in its gain, and you still want a robust control system whose dominant pole is located at a certain point and varies by just a certain specified amount in response to variation of these plant parameters, we shall see how we can use root locus to undertake robust control design. These we shall do in the next clip. Thank you.